Well, hello everyone. In this video, we're gonna cover functional forms in linear regression, which is a very easy topic in this course. I suggest that you create a folder on your desktop or wherever you prefer as a sandbox for where we keep our files for this video. So here I created this Econ4010 soundbox, and I'm going to use that to store my code and data. So if you open the functional form HTML file, we get to our course notes. So what we mean by linear model in linear regression is that the model should be linear in the parameters, more specifically in the unknown parameters. We know that the world is generally not linear. However, we can have models that are showing the effects of different things in this board parallelly in a linear form and matter in explaining our left-hand side. Anytime that we want to use the OLS model or the linear model that we have been working with so far in this course, as we said, we need to make sure that the model is linear in the unknown parameters. What that means is that the unknown parameter is that in a typical linear regression equation are these coefficients like beta 1, beta 2, to beta k. As far as we know everything that could give us those x1 star or x2 star or xk star, then we can be sure that we have a linear model which is linear in the unknown parameters. So for instance, if you look at something like this formula that we see here, yi equal alpha plus beta 1 x1 to the power of beta 2 plus the error, this is not a lot for linear regression, because although alpha and beta 1 are presented in a linear format, but beta 2 is in the power, and we cannot have any easy transformation here to make this equation linear in the unknown parameters. So if I want to estimate this formula, I need to estimate alpha and beta 1, but the beta 2 is going to be the problematic one because the linear regression model is not designed to estimate something like that. It's only designed to estimate the coefficients, and it needs some known data over there. X1 is known, but beta 2 is not known, so I don't have a known vector of data to feed in here. Another example is this equation, which I have alpha plus beta 1x1i. This part is completely linear. I don't have to be worried about it. But in this part, again, I don't know the beta 2, and my model cannot estimate beta 2, so beta 2x2 is overall an unknown term. So I have a nonlinear relationship here with an unknown parameter. So my equation is not linear in the unknown parameters. How about this one? yi equals alpha plus beta 1 x1i plus log of x2 to the power of beta 2 plus the error. Well, this one is okay. Let's see why. These are all those three equations. And you can see the unknown parameters are in a different color. In the first one and the second one, we see that the beta 2 is causing problem for us, so we cannot have a linear function. There are these nonlinear relationship that make our equations nonlinear. But in the third one, we can transform beta 2 from the power of x2 because it's inside the log function and bring it out to something like this, beta 2 log of x2i. So the new equation would be yi equals alpha plus beta 1 x1i plus beta 2 log of x2i plus ei. In this case, log of x2i is something known because we know x2i and then we just take the log of it. Now the new vector is a known vector. Nothing is unknown in it. The only unknown things are beta 2, beta 1, and alpha, and those are presented in a linear format. So that's why the third function is okay in this case. So we can have similar situations like this too, that we end up with nonlinear functions, or situations that it seems like a nonlinear function, but with a transformation we might be able to change it into a linear formula. A lot of times log transformation is the common transformation that we deal with in economic or business data. Also, we deal with quadratic forms of our data, like x. If we have a vector of x1, we could also have x12 in the right-hand side presented in our formula. So let's talk about some of the standard functional specifications that are commonly used in econometrics. One that you're already familiar with is the linear format, which is all the components of the model are originally presented in the linear format. We have, for instance, yi is linear, and then xi is also linear. So this is a simple linear regression formula. Now, the three other instances could be linear log, log linear, and double log. The order of these terms are by left-hand side and right-hand side. So linear log means that the left-hand side is linear and the right-hand side has a log transformation. Or log linear means that the left-hand side has a log transformation and the right-hand side doesn't have any transformation. It's just presented in a linear format. And double log means that both sides have log transformation. So here the first one is linear log, the second one is log linear, and the third one is double log. As we just pointed out, quadratic form could be having yi equal alpha plus beta 1 xi. That was the linear part that we originally have, and then we add the quadratic part. Here you see that the 2 in the exponent is known here, as opposed to this example here that beta 2 is not known. So in a way, we can define xi2 as another variable named z of I. So yi equal alpha plus beta 1 xi plus beta 2 zi plus ei is completely a fine formula for the linear modeling. We can also have cross products, where if we have, for instance, two variables x1 and x2 in our right hand side, we can have the cross products of those variables. We have the linear form of those variables as well as the quadratic forms of them, plus their interaction, which is the product of those two vectors. We can also have a reciprocal or inverse form, where we have yi modeled by inverse of xi rather than xi itself. One last one that we are making an example here is the logistic or logic format. I wish we could have covered this in this course, but we're gonna run out of time before get to this topic. But this format is usually being used when you deal with probabilities and you want to um, predict probabilities of an event, or um, maybe a probability of an observation belonging to a certain group, where you have a log transformation is shown here in the left-hand side of your model. Other functional forms that you could see or use are taking the absolute values of your data, or have the square roots, or you could have higher order polynomials. The quadratic term is a polynomial of order 2. You can have a polynomial of order 3 or higher. You could also have a mix and match of these functions all together. And we talk about how we can um, benefit from different hints to choose what type of functional forms we need to have in our model. One of the most famous functional transformation that we have, which is also a log transformation, is with the Cobb-Douglas production function. The Cobb-Douglas production function says that your production y at time of t is equal to your technological abilities and multiplied by your capital at that time to the power of alpha, which is basically the share of uh, capital in the production function, and labor to the power of beta. If you take the log of y of t and take the log of this part, you can have this equation down there that would say is log of production equals to some intercept plus alpha multiplied by log of capital plus beta multiplied by log of labor. As we see, if labor has a higher portion in giving you higher level of production, beta should be higher, and then if capital has gonna have more relatively higher effect on your production, alpha should be higher. Different countries gonna have different alpha and beta based on how much capital and labor are affecting their um, production. Also, A is important there, which is kind of represented in gamma over there as the effect of um, technology. We can look at that over here. If we look at that Cobb-Douglas function and take the log of these terms, we have, and in this case, the log that we are taking is natural log, so which is the base of it is e, the natural constant. So now we have ln of, or log of a, multiplied by kt to the power alpha, lt to the power of beta. But we know that when we have a product of log of product of few terms, we can have them separated by showing the summation of log of those terms separately. So then we have log of a plus log of kt to the power of alpha, log of lt to the power of beta, plus our error term. We can call log of a our technology constant, technology effect constant, equal to gamma here, just renaming a variable, and we bring alpha out. We know that we can do this with log functions. The exponent could come out and then be a coefficient. So now this ln kt could be our x1, and then same thing with beta. Beta comes out, and ln lt could be our x2, and then we have our error. So this is a completely linear function. So as we said, how can we choose the appropriate functional forms? We need to use theory and other information. For instance, when it comes to taking logs, we can able to jump ahead uh, by just looking at the data set that we are dealing with. Maybe in our data set we only have positive values, but the data that we are dealing with potentially could get negative values too. We know that you cannot have uh, log of negative values because it doesn't exist in that space, so we cannot take the log. Um, Theory is very important because it could give you hints about underlying data generating process of what's going on in uh, in the research that you have. We will have some examples of it in this video. Um, Other than that, you might have competition or a race between different functional forms or transformation, and that could give you different models. If the left hand side of your models are the same, you can use AIC and PIC. So if the dependent variable is the same, as we talked about it before, if the dependent variable is not the same for different models that you're comparing, then your residual sum of squares are coming from different dimensions, and residual sum of squares are used in creating AICs and BICs. So your AICs and BICs is gonna come from different dimensions, and you're not gonna have a fair comparison between your models. However, you can use root mean square error and on your data points, where if you have different dependent variables, um, you can make sure that you convert them in the same dimension and then calculate what would be their uh, prediction for your data points. And then because they're in the same dimension, it's fair to compare them. Speaking of paying attention to functional form of the dependent variable, when we have log form on our left hand side, there is one important thing that we have to remember when we want to basically have our prediction or estimates for the original value of yi, or in other words, the level form. Yi itself is in a level form, and then if we take the log of it, log of yi is in a log form. So suppose we want to estimate a log linear function like this. It could be double log too, but because the log of the right hand side, for instance, if you have a log of xi, we transform that into a new variable called zi. So it's a very similar case. So for simplicity, just imagine a log linear function like this. We have log of yi equal alpha plus beta xi plus ei. Our goal is we want to find yi hat. Once we estimate this model, it's easy for us to estimate log of yi hat, which is alpha hat plus beta hat multiplied by x. Now, in the first step, we could think that, hey, this is a log of yi, so if we take the exponent of exponential function of this, then the log gonna go away, and then we're gonna end up with yi hat. That is, yi hat equals to exponential function of log of yi hat, or log of yi hat, and then that is equal to exponential of alpha, exponential function of alpha hat plus beta hat x. However, this will systematically underestimate the expected value of y in this case. We can show that actually the expected value of y given x is not just exponential function of log of yi hat, but also it needs to be multiplied by this correction term. So this correction term is basically is exponential of sigma hat squared divided by 2. You don't have to learn how to prove this, but it is important to know that, because if you want to compare linear model with a log linear model, then you need to make sure that you make the right transformation, and that is what we want to do in this example. So the example that we have here, gonna use the wage race data set that we have worked with in one of our assignments. So you can go and open the RMSFE example file, and it's going to go to RStudio. So as you remember, let's read this data set. We had a data set of 206 observations, and we had wage, education, age, and gender, and a couple of race variables. As you see here, it seems that wage looks like to be like an hourly wage. Now, in the example that we had in our assignment, we had the independent variable was only wage on the left-hand side. Only in your bonus questions you were asked to comment on what could have happened if the left-hand side would have been the log of wage. So we covered that a bit in the class, but here again, we want to compare these two models correctly after applying the right correction terms that is explained here. So what we want to do in the log linear model, we want to estimate the model and then estimate the estimate the alpha hat and beta hat in that model, and also estimate the sigma 2 hat, and using that find out what would be our actual value for our estimate, which is not underestimated systematically for the y variable. So what we need to, as we said, estimate alpha hat and beta hat, and for the sigma hat square, we need to find the residual sum of square of our model divided by degrees of freedom. Pretty easy. So we read our data set, and here we are setting up some parameters to show two plots in the same window over there. And first we want to look at density of wage. This is what we looked at before. I forgot to run line, so run it again. And you can see that we don't have that many wealthy people or people who are getting paid with a higher wage rate, and it's more skewed to the left side. But if we take the log of that and then look at the density again, now you can see that we are dealing with a more normal shape. Usually stuff that are showing their distance in power, like wealth or income or price of a house, if we take the log of them, we end up with more normal shape in our density. I'll use attach function here and then name of the data frame, which is table 1, to quickly create the variables that are existing in my model. And so I don't have to define one by one. It's just one variable that I want to define it, and that's log of wage, which is just the natural log of wage. Now I make two models. The first model is using wage as left-hand side, and the other one is using log of wage, and both of them use the same variables on the right-hand side, that is education, age, and gender. So now we can look at the summary of our models too. This is summary of model 1, and you see that all variables are pretty significant. This is the best model that came up with in our assignment, and for model 2 as well. Those are pretty significant yet too. However, yet we cannot really compare these two models if I want to get AIC or BIC, because the left hand side are not in the same format. And that is what we were talking about over there, that like you cannot compare stuff like that unless they're exactly the same in both models. Now I can get for model 1, I can get residual sum of squares in general to see, okay, what would be the residuals. That is, what is my, when I have simple model of y equal alpha plus beta xi plus ei, my residuals would be yi hat minus yi, that are kind of estimates for these error terms. Now, if I get sum of squares of those residuals, or residual sum of squares from model 1, that could be a goodness of fit measure for me. So we end up with the number 3580. That means that if I do the same thing and that for model 2 and that number is smaller than this, then model 2 is better. If that number was larger, then model 1 is better. Now in model 2, I can just do the wrong thing first, that is, not applying the correction term, and just take the exponential of the log of yi hat, and that is getting exponential of m2 fitted values minus wage and to the power of 2. So if I do that, I end up with 3676, and that number is larger than this number. So if we really didn't know what we were doing, we would have choose model 1 so far, because 3580 is smaller than that. But we know that this is not the right way. We need to improve our calculation by applying the correction term. So the residual sum of squares from model 2 would be the sum of the squares of the residuals from that model, so we can get that. Why do we need it? Because as you see in this file over here, we want to calculate sigma square hat, and that is coming from residual sum of square over degrees of freedom. So in our R file, we got the residual sum squares. The degrees of freedom is number of observations minus number of parameters that we have in the model minus 1, or number of variables minus 1, minus k minus 1. So number of variables that we have are 3, so that's minus 3, and then minus 1 is always in the formula. So now we have our sigma hat 2 and our sigma hat squared, and now we have that correction term, and if we multiply that by what we were actually trying to calculate over at the top, we have our converted y hat that are converted correctly because we applied the correction term exactly as it is mentioned over here. If you want our y hat, this is the formula. So that's what we used in this line of code as well. So we get our converted hat, and now if we have our converted y hat minus the actual values for y, which was wage, and then get that one, we have the true residual sum of squares for the second model that is in the same dimension as the first model. Now we can compare those two numbers. Let's go back up and then run the residual sum of square for the first model. So we have in the same screen again, 3580, and we run this, nice, 3511. Now we see that after we apply the right correction, that number is smaller. That means that model 3 is actually more efficient in explaining the base variable. So that was an example of how to predict our fitted values when we deal with a log functional form for our dependent variable. Sometimes when we want to compare multiple models, we can use the root mean square error comparison between them. But instead of doing the comparison with the data that we train the models with, we can actually have the comparison on a sample that hasn't been used in the training of those models. We call that out of sample root mean square error or root mean square forecast error. Typically, you can divide a data set to a train set and a test set. The train set part of your data is a sample that you use to train your models. And after you have your models, in order to compare them, you can go to the test set and just acquire the predictions from your models for the test data and then see what kind of error you get if you have the square of those errors and then sum them up and divided by the number of observations, you get the mean of the square of your errors and your forecast error, and if you get the root of that, you will get the root mean square forecast error. So in the first step, you need to divide your data set. Typically, you do 10% or less for your test data, and then about 90% for your train. 80-20 is also possible, especially when you have a lot of observations. But usually when you don't have a large data set, you want to use that information to create your models or train your models, so you can't really allocate a large portion of your data to the test part or the out of sample part. Anyways, imagine that you have total of n plus h observations. You can use the first n observations in your training part and then use the final h observations for your prediction part. Then the predicted values for index from 1 to h in the test sample gives you the observations, actual observations that were not used in the model. Then you can use the predicted values by hats from your models and then calculate the root mean square forecast error for any specific model that you are working with. And then at the end, you can compare those numbers. It's pretty similar to what we did over here. The only difference is that if you're working with the log model in this case, when you're working with the root mean square error for the out of sample data, because in out of sample data you don't have any sigma squared in your model, or you haven't defined that, so you don't have it. You just use the first part. So that is very similar up to what you got already up to this step. Anyways, but if you don't have the log transformation, you don't have to be worried about it, any of these correction terms anyways. And then whichever model give you the lowest value for the RMSFE is the model that you want to go with. Before finishing this part of our course, the functional forms in linear regression, by talking about fitting polynomial functions, we have another example that we want to talk about. You remember that we said how can we figure out what type of functional forms we need to use. One of the items that we talked about was theory, or thinking intuitively what you're dealing with. One of the examples that we are dealing with these days is the COVID-19 virus. So there's a data set that we have in the sandbox, and we also have example, COVID-19 example, R code that we want to review right now. So that's the data, COVID-19 data.csv. We go to this example file. So what we are doing here, let's clear up all these guys. I press Ctrl L here, clear up my console log, and now I read the CSV file into DF as my data frame object. If you look at this data frame, I'm gonna close these guys too. If you look at this data frame by clicking on that icon, we see that we have some kind of ID and observation date. Here is the province or a state, so one level of locality and then another level of geographical location data, which is about country or region, and then a date of when was updated the data, and we can see that this data for that date was just updated the same day. Sometimes it could be different hours, but that's not the column that we are interested in. We have the confirmed number of cases and then death and recovered. In this case, we are just interested in confirmed numbers, and we want to look at the US data. So what we're going to do, we use this line over here that we said will give us the DF data frame, but just only for the rows that the country or region is equal to the United States. So after running that, our data frame is just including the US data. Now, and we are also, for this assignment, not interested in the granularity level by state, and we want to look at the overall US data. So what I want to do, I want to aggregate this data by date and then just have the total number of confirmed by date in the United States. So in order to do that, I first need to make sure that the type of the observation date, the data type of that is date and not something else. these are tiny stuff that sometimes could be really cumbersome and uh, you know painful, but we have to take care of them if we want to keep everything neat and tidy. So here you can see that observation date is factor. I don't want that. I want it to be date. If I run this line of code, now it's changed to date. Now I can use that attach df to create the variable names in the background. So now the variable names are created. I create these two data frames, each have just like one variable. So I have days and observations. The days just give me the observation date, and then observations are actually the confirmed numbers. So those were the two only columns that I wanted to work with. So that's why I'm only grabbing those. And now I'm saying aggregate the observation numbers by days. So it looks at if it has like two January 29th, and there are two numbers there, it sums those two numbers, and there's only one row for January 29th. So I have total number of confirmed cases for that day in my data frame. So I create that, and then that would be aggregate data frame AGGDF. If I look at that, now that's a summary of our original data set, has the dates here, starts from um, January 22nd. The first observation was recorded in the United States, and then goes up to March 24th. This is as recent as the data is, to 53,740 cases. So let's get the number of observations. I have 63 number of observations. I can plot my decorate these guys. Oh yeah, I need to attach aggregate df2 to basically be able to use the variables in that data frame too. I have variable day and observation. I had done that, so that's why I got that error. Now I should not. So do that, and just got the just points. That's my data, and now I could do the just like show the same thing with some lines. So if you look at this, this is what we're talking about. When I'm looking at some data like this, I'm like, okay, the first thing I know that I don't want to, this is an exponential growth. We all heard that. So exponential growth, that is like one of the situations the log transformation is going to take things, change things to more linear form. So, theory or intuition, this data visualization helped me to figure out that, oh, maybe log transformation could give us a better view. Now this is a log transformation of the same data, and if I look at that, you can see that here I don't have that many observations. This is a log form of it, so up to here is like 100. I'm sorry, not 100, because that's with a natural base. Anyways, low number of observations, probably like it hits around 100 over in this region, and then we can see that it's going up, well, kind of like a linear, very very linear form for this region for a while, kind of like late February and forward. So this also helps us to see that, yeah, definitely log transform is making things look much better. Now I want to create a new variable, and then call that what was the previous day number, and for that, because that means that if I'm here, In the second day, the previous day number was 1. In the third day, the previous number was 1. In the fourth day, the previous number is 2. And I should just like go forward like that. Of course, for this first day, I don't have anything available. So the first day I have NA, and then for the last day, my number would be just a 62nd row, not the 63rd row. So that's why I'm having observations from the first row to the 62nd row, and nothing available for the first one. Now I add previous day number, and if I go look at that, I created that value. I'm doing that because what I'm interested in is what's the ratio between 2 consecutive days, and that would be what's the growth rate between 2 consecutive days. The larger the growth days, it's faster the pandemic is growing. So now, because the first row is not available for one of the observations, I dropped that and I just used the second row forward. Look at the data set, I don't have that anymore. Now, if I get the log of the observation for today divided by previous day, that would be the ratio, log of the ratio. So I call that log ratio variable, and created that variable. And now I have log ratio variable that is created over there. Now we can recreate the variable names again in the background, and I want to plot the log ratio and see how it looks like. So when I look at this, the variance is very high in the beginning of it. The reason for that is number of people, number of confirmed cases are low. They're scattered in different locations, so you can't really expect that it has picked up any specific pattern. However, when I pass that late or get to late February, final week of February, it seems that we start to have larger numbers and the pattern is showing up. So I can just neglect this part, and for the rest of this study, just look at these points ahead. So what I do is I'm only looking at the observations that are in month of March, and now my data frame going to be smaller than what it was before, and you see it starts from 76 with 70 the previous day, so very close to 100. The second day it's turned to 101, and now I use attach again because I changed my data frame, so now I have new variables with the right number of observations. If I want to plot it, and this is what basically we've been seeing. Now the new number of observations is right here is 24, and now what I want to do, the ratio is the important variable for me because it's the ratio that if it's high, then I have a fast pandemic. If it's low, it means that it's more controlled compared to a higher ratio. So I want to compare the ratio. I want to say what's the today ratio compared to the yesterday ratio, and I can look at that, and basically those two could be now my new y and x's. So I can plot this x and y, and those are the points. I can have a simple linear model today ratio given the yesterday ratio with a summary of it. I can see that the intercept is really important, so some average level, but the coefficient, the negative coefficient for yesterday ratio is not that significant, but nevertheless, we are Bayesian, so we are not just neglecting everything. We see that there is a tiny negative effect on whatever ratio you had yesterday to come to today's ratio. But more than that is this intercept that is showing for the period that we're looking at, that's on average what's the daily ratio of change that we see in this pandemic. So I can have some lines, but going back to going back to the original plot, which is basically this. I want to see what's the prediction of my model for this plot. So now I have the points and I have the prediction. So this is basically the prediction that is coming from that model. You can see that is kind of like hovering around 0.3 log of the log ratio of 0.3, and I can actually have the actual values shown over there too. So what we see here is that's the actual fluctuation of ratios between 2 consecutive days, and this is the average that is coming from our model. It's kind of showed that for the month of March, it's been averaging around 33% for the United States. If I get the log of 1.33, that is like if the ratio of 2 consecutive days was like every day is like 1/3 more than yesterday. So I can show that line as well with the color of blue, and you can see that my data is kind of like around that. So that was just like some simple example of how variable transformation could give us better understanding of data that we are studying. If we were just sticking to original data that we had here, we really didn't have any chance to have some meaningful um, description of what's really going on. We did this time series example. We did with the log conversion. We made everything much better, but in your time series section, you learn that this is non-stationary data. So what we are doing with the log ratio part, we are turning the non-stationary data to a stationary, and then we only work with this part of the data set. Anyways, going back to the course notes to finish the functional forms. So one last thing is fitting polynomial functional forms or polynomial functions. So one example of it that we talked about was the quadratic function. It's a polynomial function of degree of 2, and it has the linear part and the quadratic part. So most important thing is that if we are comparing different polynomial functions and we end up, for instance, we compare the model that has a quadratic term but doesn't have the linear term, and we compare that with another model that has the quadratic term and linear term, has both of them, but the model with only quadratic term ends up to have a lower BIC, for instance, or AIC, and we want to choose that one without including the XI. Well, this is what we're talking about here that we should not do. So if we end up with a in our polynomial function, if our in the hierarchy of the terms, if the highest order end up to be significant in the model, we need to include all the other orders before that one too, although they may not be significant. So let's look at this example over here. For instance, let's say we have these three models. yi equals alpha plus beta 1, x1 plus ei. This is a simple linear regression. And then another simple linear regression, but just has the quadratic term. So y equal alpha plus beta 2, x1 squared plus the error term. And then the third one is yi equal alpha plus beta 1 x1 plus beta 2 x1 squared plus the error term. If you look at the AIC and BIC, these are just arbitrary. So relatively, we just want to see which one is smaller. So if you look at AIC 236 is the smallest one, BIC 231 is the smallest one. So going by AIC and BIC, second model should be the best. But what we're talking about is that because this highest order in this polynomial function of second order, which is a quadratic function, it is significant, and you want to include it in the formula. And overall, this equation ends up to be better based on AIC BIC. You said, wait a minute, don't go with that because it hasn't included lower term before that one. In this one, although you don't end up with the best AIC and BIC, they are still better than what you get in the first equation. But because you have included everything in every terms, then that's the best model to choose. This is very similar to something that you see in the time series analysis when we are talking about including the lag of a time series variable. And if we end up to include the fourth lag of some time series variable because it's significant, we will include the other lags going up to the fourth lag as well, although those lags might not be significant in our model. So that's the most important thing that we're talking about when we are fitting polynomial functions, that we always fit the terms of a polynomial model in a hierarchical manner. So for instance, if you want to figure out fourth order is appropriate, or if a polynomial function with an order of 4 is what we want to go with, we first check if the fourth term is significant. If it was significant, we have to include all the other terms before that as well. If not, we go to the third one and then do the same thing till we get to the first one that is significant. So for instance, in this example, the second one was the significant one, so we include the ones before that even though they might not be significant. So that's why we choose the third model, because it includes all the orders. Well, this is it. This was the end of the functional forms in linear regression. Thank you.